Hello, I'm Chuck.
I'm Hampton Smith.
And I'm Heather Hartman, and we're working for the Resolve Software Research Group at Clemson University.
And we're here to present and discuss the Web-Integrated Component Development and Reasoning System, seen here. This online system, developed and maintained by the Clemson RSRG, was created to provide a component development and mathematical reasoning environment that was freely available and designed to run fully within the user's web browser. The user interface for the system is written in HTML and JavaScript, providing cross-platform support without requiring users to install any browser plugins. The system uses Resolve, a combined programming and specification language. There are 4 types of components in Resolve: concepts, enhancements, realizations, and facilities. Concepts and enhancements are similar to Java interfaces and contain both operations signatures and specifications. Realizations are implementations, and facilities are used to instantiate and use the other types. Components are organized intuitively according to their relationships rather than by their file system locations. The user interface offers a large body of example components, extensions, and implementations, and provides support for user-created modules. Now let's take a look at the specification for a queue, which can be found in the concept queue template. Separating specifications from code keeps verification modular. Clients depend only on the specifications of their components. This queue uses a generic entry type and is bounded by a maximum length. We model queues as strings, that is, finite sequences, and provide a suitable constraint. We provide the usual pre- and post conditions, but also include parameter passing modes, which summarize the effect an operation will have on a parameter. Here we see that enqueuing an element alters the value of the element, because we may steal it to prevent an undesirable alias, and updates the queue, since we intend to change it.
Now let's look at an enhancement to the queue component. This one appends the contents of 2 queues. Note the clear demarcation between mathematics and programming. These operations all operate in the mathematical model rather than the programming representation. Here's an implementation. We'll get it verifying in the background while we discuss it. Because we verify against the specification of the queue alone, this procedure is independent of the queue implementation. We require a minimal set of annotations to our while loop to ensure termination and express the logic of the loop. By clicking this tab, we can return and watch as Resolve's integrated minimalist prover finishes up. Our prover is primarily a rewrite prover with an emphasis on flexibility and generality. Notice that we could return to the code and break it, then verify again. Resolve will spin its wheels on one of the resulting verification conditions before ultimately giving up.
Now let's consider a more complex enhancement to sort a queue. This sorting capability sorts a queue according to a total pre-ordering LEQV. The ensures clause of the sort operation states that the updated queue's order conforms to LEQV while remaining a permutation of the original. Uninterpreted predicates like these increase readability and result in easier to prove verification conditions. Here's a selection sort implementation. It is important to note that to instantiate this realization, the client must provide an implementation of a compare operation that verifies against the specification given here, providing a procedure for accomplishing the LEQV comparison. This code will create various verification conditions, which can be overlaid on the code by clicking this button. For example, we see that one is generated to show the post condition of each implemented operation holds.
A data structure specification doesn't do us much good without associated implementation, so here we have one based on a circular array and another based on pointers. We generate verification conditions for each that permit us to verify it against the specification. Resolve does not use specialized machinery to reason about arrays, pointers, and other constructs that are often considered primitive, so we draw their behaviors from a specification like any other component.
In addition to the reasoning capabilities just discussed, the system can also translate Resolve programs to Java executables. The user interface contains several example Resolve programs, known as facilities. Selecting a facility, then clicking the Build button, translates the facility and any other required Resolve components to Java source code, which are then compiled to Java bytecode and combined into a single executable jar file. Upon completion, the jar can then be downloaded and double-clicked to locally run the Resolve program. The environment has been publicly available online for more than a year. It has been used both here at Clemson and at other institutions for graduate and undergraduate research projects and for undergraduate software engineering coursework. Students have used the interface for both Resolve component development and software reasoning and verification exercises. On behalf of all the members of the RSRG at Clemson, I'd like to thank you for taking the time to watch. For more information or to try it out for yourself, please visit our group's website.